Okay. I have quite a few mistakes, like I didn't connect to Tulsa last. Uh, this Tuesday, but hopefully I won't make this mistake again. I just sent that. I created email list for you guys, like Tulsa and Norman. Then I just sent to you, like in Norman instead of sent to Tulsa. So I basically erased the group for you guys. So next time I definitely won't make the mistake. So and also like for Canvas, if you guys check Canvas earlier, that there was assignment just to put in your abstract, like presentation abstract, and for the default is basically didn't have a submission for a abstract, Canvas assignment. So I forgot to add that. So I added that back now. So that so-called abstract can be very simple, like just a paragraph, like a couple sentences. Okay, I just want to um, um, kind of the initial intention is like to force you guys to think about these stuffs earlier, but I think you already did. So anyway, it doesn't matter, I guess, that much. So anyway, we talked about the general neural network last time, and we'll start talking about CNN. And just maybe wait a sec, maybe I will just use a Suno thing. So I assume, like, okay, how many of you heard of CNN? I guess most of you, right? Convolutional neural network. Yeah. So okay, CNN is a why I cannot. Okay, this is always my when getting old, my brain is not working. It's supposed to be. So CNN is a convolutional neural network. Convolutional neural network. So just the name suggests that you will expect there's some convolution, like operation, that if you remember in cell processing, like convolution is just something like you have a signal fx, let's say you have a filter like gx, then the convolution is like something like fx, like g, maybe something like that, right? And take an integral or summation, sum over x pi, stuff like that, right? That's the 1D convolution. And by the way, just a kind of remark here that the convolution in CNN actually is really a correlation. So in convolution, you really have the filter, you flip it, and then you do a dot product of your signal. So, or you can think of that like if I have a signal here, 1D signal, I have a filter, something, maybe this is a filter, maybe I just make up a filter, something like that. I may make it not symmetric or something like that. So my convolution, or the so-called convolution, is really a correlation. It's basically if I compute the convolution at this point, it's just like I have this region here, right, and do a dot product of this guy. So in the sense that you can think of this multiplied by this guy and take an integral, stuff like that. And that's basic convolution. And this is 1D convolution. So if you are in 2D, actually typically it's used in more often in 2D, but of course you can do 1D as well. In 2D, then basically you have a filter patch, right? If you think of like image processing or something, like you have an image, you have a filter patch. For example, a Gaussian filter. I don't know how to draw it. Or maybe I put in some values here. So maybe just a 3 by 3 filters. Maybe I have value something like 0, 1, 1, 1, 2, 1, 0, 0, 0, right? So then my convolution, for example, here I have a particular patch here I have some value like 5, this is like 10, this is 10, 5, 5, 5, 5, 5, 5, something like that. Then the convolution at this point, convolution, again, like I want to put a quotation there because it's not really in cell processing, the definition of convolution. It's really a correlation. It will be like just a dot product of this patch with this guy. So then in this sense, here will be just equal to what? 2 times 5 plus, what should I do? Okay, if I do this multiplied by this like element wise, I get like 0, 5, 0, 10, 10, 5, 0, 5, 0. Then we'll just sum all the values together. Then there will be like 35. Yeah, that's basically it. So nothing magical, really. So that's it. Maybe so what's so interesting about this is like, okay, one remark I didn't emphasize. As you can see, like, the filter is like fixed, right? Here, this filter is like is shift invariance. If it's not shift invariant, it will be something like if I apply the filter here, if I consider region here, maybe I will have another filter. Let's say my filter will change to from this guy, change to maybe this. Then in that case, it won't be shift invariant. Or like if I have a filter like this, but if I move to here, I have a adaptive filter become like 0, 1, 3, 1, 2, 2, something like that. Again, this won't be shift invariant as well. So the assumption here is like you have the filter is basically fixed. So it's like in classic cell processing as well. So then what's the difference of like neural network from the classic case? The biggest difference is that in classic neural network, classic cell processing, this filter is fixed. Where you design a Gaussian filter, you design a whatever, but I don't know. I don't remember filter design anymore. You guys are much more familiar with filter design than I do. Like this is like I didn't touch this again like since I undergrad, so 20 years ago. So, but like for CNN, basically this filter is like trained by your data. So you don't know what is that filter yet. So you just assume this is like some unknown here. Then given input, output, and again you can do train end to end, stuff like that. So I guess this is an introduction of my CNN. Then I guess maybe I'll go to some of the slides here. I guess I'll skip this one. People, when they talk about CNN, they like to refer to this word Hilbert and Rizzo. I guess you can go online and look at the video for that. This is like some fellow from medicine that they eventually get a Nobel Prize in medicine for the work. Is like they poke into the cat's brain and try to see like how does it respond. I mean, individual neuron to see like how does it respond to like visual stimuli. And by accident, actually, they try to let the cat look at lots of different stuff. And by accident, they find that like it's not just, okay, they basically see that like they can have lines, like certain neuron kind of sensitive like to lines, to edges like this, to line. But it also depends on the orientation. For example, here, like you have no stimulation if the edge is like that, but if you shift a little bit like this, then you have like lots of stimulation. But if in another orientation, then you don't have stimulation. Stimulation, and then like they also like find that there's some hierarchical structure, like you can group those response in one region, and then it's just like hierarchy. Like they find some hierarchical structure, so that gives them idea. They think of like, okay, we have like different level of neurons. There's like simple cell, then have more complex cell, and then like even more complex cell to it's like, actually, if you look at what people kind of take this as an analogy for convolutional neural network. So, although I want to say that I recently listened to a kind of conversation or like interview of like a good fellow, he thinks that like many people don't kind of like researcher believe in this anymore, but still like I guess many maybe have like interpret that like maybe the neural networks. If you look at the neural networks, maybe I just jump into some of these slides here. I think I have one of these. Jump pretty much ahead. Let's see. I cannot find it. Maybe this one is good. So you just have like layer of neural network. Right? So you have like conv layer, and so on. So the lower layer you can interpret as like kind of neurons responsible to extract like the lowest level features. For example, just edges, corners, and so on. And as you move to higher and higher layer, they will try to extract more and more complex features. For example, like you can see a wheel of the car there, or you can see a face there, and as you go into higher layers. But let me just go back to what we had earlier. And actually, another work that people usually require too, like for CNN, would be like this neural cognition, kinotron, I don't know, maybe there's a typo here, I'm not sure it's neural cognition, by Fukushima, a Japanese guy in 1980s. So he basically have something very similar to a CNN already, but he didn't have a training kind of mechanism. He didn't use a backpropagation to train the model, and later on, of course, like backprop is kind of like popularized in 80s and 90s, right? And it was reinvented by many fellows, and nowadays, I guess like for CNN, many will part the kind of like the father of CNN to LeCun, like he basically was in AT&T like in 90s, and he kind of like probably he's not the first one to have the idea, but he's the one successfully applied that to a real problem. Basically, they have a kind of digital recognizer just to write the postal number, and they got this data set from like the post office, and they're trying to recognize each of the digits to whatever something. And they basically build a very primitive, or not I shouldn't say primitive, a CNN model. So after you have the alignment and you figure out the number, like do the segmentation, then basically just go for CNN here. So, and okay, basically it will have, as I mentioned, some conv layer here. The conv layer will be just doing convolution, and then you have activation and conv layer, and finally have some fully connected layer. I will go into more details to each of these layers here. And but here just a couple high level history. And other work like people will give lots of credit to is like the work like by Hinton's group like in 2012, the ALICE-LET. That was the work in ImageLET, where they have this competition every year, like for many years. So you're just doing like multi-classes image recognition. So you have 1,000 classes, like 1,000,000 images. You just want to like tiny images to recognize each of them to belong to which group. And this is like the first work like using kind of like neural networks. Recently, the works in 2011 is using like kind of like shallow networks. I guess I mentioned that like at the beginning of introduction. And there are many other applications of CNN. Actually, everything you can imagine with like there's an application almost someone already did it. There's almost like apps like just want to invent the apps like for iOS or Android apps, then like whatever you have the idea, someone already did it, almost like that. So for example, you have classification is typically you have an image, you just want to figure out, have one object there, so we just say what is that object. But you have like more complicated problem like detection, you want to also make the bounding box of that object. And even more complicated will be segmentation, right? You have, for example, here you want to, for each pixel to recognize whether it's a person or like it's a ground or like trees and so on. Of course, like this kind of used a lot in real-world application. For example, like autonomous driving, you need that to identify, okay, that's persons and cars and so on. And there's also hardware, like for example, this is TX1, now they have TX2, and what's the latest one? I forgot. Have a half year? I forgot. I think it's that, yeah. And also, let's see what. Yeah, you can do some. Yeah, okay. I think this is a face recognition, or you can do some pose estimation. You can estimate the pose of some person, and you can like do a computer game. So just trying to train your network to. Of course, this will relate. Also, besides CNN, we'll need to use some reinforcement learning techniques as well. By the way, how many of you know reinforcement learning or like work on reinforcement learning before? This is another hottest topic like in recent years. I may talk 1-2 lectures in reinforcement learning. That should be fun because there like you can talk about robots or like design like a model or like train a lecturer to play computer games and so on. And there's also lots of stuff like medical application, kind of character recognition, and so on and so forth. So, okay, and also like that's I guess we mentioned like captioning, like you have image captioning, and you have something reverse also. For example, if you combine with GANs, you can we'll talk about that later on. You may give a sentence and try to reconstruct some image with that sentence. And CNN basically is a component for all of this. And also like this is, anyone know what's this? Like, anyone saw something like this before?
Seen one where they feed a bunch of artworks into it and it generates new ones.
Yeah, I see. Actually, this one they didn't even need to fit artwork. They just use the image flat model. You can do something like this. We can talk about that later on. So I also already go through some of this like. So CNN, yeah, just you have convolution like the classic neural network, right? But I also miss out some caveat there. So unlike classic signal processing, there besides the filter is trained, also like in classic convolution, usually even for 2Ds, we are typically considering a kind of like a 2-dimensional filter, right? But in CNN, even you consider something 2D is really 3D. So for example, like I start with an image like that. You essentially we have like 3 color channels, right? So each of the filters I can, therefore, in a sense, if I have a filter, let's say a size of 5 by 5, actually I also by convention, my 5 by 5 filter is actually referred to the 5 by 5 by 3. That's the number of channels there. So basically, I'm doing a dot product of this volume with like a volume in this image block here. And then, so this is just an example. Then, as this filter just kind of move around in this image block, then I have like many numbers, right? And this gives me one activation map here. So as you see here, for example, my filter size is 5 by 5 high, 5 by 5, then I will basically get an output size like 28 by 28 by 1, right? Why 28, by the way?
Because it's 5 by 5.
Yeah, kind of. Yeah.
Moving over 1.
So we have the boundary effect here if we don't do any padding. So my kind of filter go all, to the edges. So I can only start from index number 3, let's say. I cannot get earlier. So therefore, like on both sides, I will have like 2, kind of like I need to reduce by 2. Therefore, like it'll be like 32 minus 4, so I will have 28. So of course, if I do padding, then I can keep 32. For example, if I pad some zeros, or like I may use reflection to do padding as well, but padding 0 is more common, honestly. So if you pad like 2 zeros for each of the edges there, then I will get back to 32 by 32. So, and this is just one filter, right? I can have multiple filters. So if I have like many filters, let's say, I can have a stack of filters. For example, like I have 6 filters here, then my final output will be like 28 by 28 by 6. So, and this is basically doing the convolution, right? This is just a linear operation. So we want to introduce the nonlinearity here. So it can be some activation function that we mentioned before. For example, we can just use ReLU. So after this linear operation, we can just apply ReLU there. Then we can do this again, right? Have this another convolution and ReLU, convolution and ReLU, and so on. And oh yeah, this is the image I want to show. So for example, like if you try to train with your some input image, and when you train end to end. Oh, by the way, like how do I train end to end? So if I have what's the loss function again? Just you should know, but I just want to check if you guys remember. For example, if for ImageNet for classification, what should be the loss function?
It's like mean squared error or something?
That is for regression. So, okay. First, I probably should ask, like, let's say if I have okay, just like ImageNet, there's 1,000 classes. So, what's the dimension of the output? At the very end there. So this I think I'm not using Suno here. Let me also open a. So for example, like I have finally the output will be something like a vector. So let's say I have 1,000 classes here. So the dimension of this, what is the dimension of this output here? It should also be 1,000 classes, right? So my output here, typically for a classification problem, this will output my distribution, right? Something like, given the input, what do you think about the probability for each of the classes, right? Given that output, so it's like I get a distribution, something like, right? And then the loss is the cost entropy loss, right? If you remember, so it's something like if I have this, of course, this value, this something here. If I just have a very end, it's just a fully connected layer. So this value will be unbounded or like some just arbitrary number. I should go for a softmax layer to make this is looks like a probability, right? So I should have a softmax layer here in the middle at the very end. And then this one now is like just like a probability distribution. So something P given the input, let's say this is X, like what's the X like? So actually this is not a good way to write it. Maybe I should say PC given X, what's the probability for each of the classes, right? And then like I should have, then the loss will be just a kind of the cost entropy loss is a QC log PC, right? Something like that, sum over C for all the classes. And QC is basically the ground truth, right? So it's like a delta function. If you know for sure that it belongs to that class, then it's a delta function, something like that. So and if I hold that, okay, then I minimize the softmax loss. Oh, sorry, this cost entropy loss. Then I train end to end. I will get something like this, as I mentioned. So you have lowest level, you have more or less edges and corners, like some weird stuff. Mid level, you see something more interesting. For example, you can barely see this is looks like some wheel here, maybe a wheel of a car, and some different things. And then you go to higher level, you have like more complex structure. You may even find a phase or something like that. Yeah. And let's see. So this is just repeating what I said like about padding. So and there's some slight modification. So we can do a kind of convolution without downsampling. Basically, for each of the pixel, we'll do a filter there, or we can do a downsampling, that's so-called stride, that we skip every other pixel, for example, or that we have a kind of a terminology called like a stride there. So when stride is equal to 1, basically we are not skipping anything. So when stride is equal to 3, we are skipping every kind of like we skip 2 pixels for every pixel, basically. Stride equal to 2, then you skip 1 pixel for every pixel. So for example here, this will be stride equal to 2, right? So if I stride equal to 2 here, then I will just get like the output then will be just 3 by 3, right? If my filter is 3. And then if my, okay, what is that? When stride is equal to 3, then we skip every 2 pixel here. So I will basically, next one will skip to here. So then it doesn't fit, but then in this case my output is like, depend on the paddings. It may be 2 by 2 or you may get 3 by 3 or something like that. So this is like very simple, like you can easily figure out a formula. So for different padding size, the dimension of the image, filter size, and the stride, you can kind of approximate the size of the output. So this is very simple. I mean, like you don't need to remember any formula. You can just figure it out yourself. And of course, like the size will be affected by the padding, and this is kind of obvious. So this is just some very simple exercise. That's check with your understanding here. Like, so I have the input volume here is like 32 by 32 by 3, and the filter is like 5 by 5. I have 10 5 by 5 filters, and stride is equal to 1, padding is 2. Then what is the output size?
32 times 32 by 5.
By 5.
Or, maybe 10.
Yes. Yeah. You have like 10 filters here, right? There's like 42. Yeah. You do your pad 2, so you strike 1, so it's just you if you don't have any padding, then it will be 20 by 20 like before, because you have like pad 2, then you get back 32 by 32. Yeah. So I say by 10. And oh, by the way, like this, how many parameters for this layer? Can you count the number of parameters here?
That's going in or that's coming out?
In the middle. you have this operation, right? Yeah. You think of like how many. Yeah. It's not a tricky question. Okay, I make it like a tricky question. It's not a tricky question. So, I have that filter. It's 5 by 5, right? There's 25 of them, right? So I have 10 filters. It's like, okay, the less accurate answer would be just 250, right? So I have 10 filters. Each filter is like 5 by 5, right? So all of these values there in that 5 by 5 can be trained. Yeah. So I have like the filters like this. Oh, I don't know why I draw like, I'm sorry, I didn't intentionally make it like weird. So let me draw back like better. So this is what, 4, yeah, 5, right? So I have 25 values for each filter here. But more precise should be 26 because there's a bias there. We didn't. So supposingly you have a dot product of there. I didn't mention that I should have a bias there. Just you can basically say this. Okay, I block here. Kind of a dot product with this guy. Oh, where's that guy? I made a mistake here even. There's 3 here, so that should be 25 by 25. Or sorry, 25 by 3, because this filter is really volumetric, right? Yeah. So this is like this block here. Kind of do a dot product with this guy, and then I will add the bias there. At 1, there's a bias term there. So therefore, like each filter will have like 76. So you have 10 filters with 760. And so this I don't want to read this. This basically is the same thing. Let's see. And one thing like this is another remark that is pretty different from conventional kind of convolution, right? Because as I mentioned, conventional convolution is really 2D, and this one is really volumetric. So therefore, in conventional, you don't have 1-by-1 convolution, right? It doesn't make any sense. But here we can do 1-by-1 convolution. So 1-by-1 will be just like I take a tube basically and do a dot product of this tube with some filter of like a tube filter. And then you get one value there. Then I can apply like here like 32 filters. Then I will have like 32 of them. So maybe I will ask you again, how many parameters here? Like, yeah, actually, there's a number here, but of course, it forgot the bias. It doesn't matter. It's tiny. In practice, it's good to know this worth counting sometimes, because when you need to debug actually why your kind of your memory is a leakage or something like that, maybe you it's good you get back to that one. Just of course, yeah. But, so in this case, like each filter will have like 65 parameters, so it will be 65 by 32. So this okay. This is just some example code for a layers. But this is kind of outdated. I won't get into detail for this. This is in Torch, for example, the original Torch is in Lua, right? And Caffe, I don't know if any of you are interested to present Caffe. I think I didn't receive any request for that. And I guess Caffe is losing its popularity now. And there's also like Lasagne. I guess no one uses it anymore. So I guess I think I can skip this here. Okay, so another very important component to mention is the polling layer, right? And the so-called polling layer is just a downsampling layer. So you have basically all the operation we mentioned here, the filter here. Of course, you can do downsampling in the sense you can extract also, but at least by kind of tradition, or like and also like I think like people still use it in the lectures. You can do a downsampling using this polling. Polling is like probably the most common type is just to do a mass polling. It's just for example, if you have a 2x2 mass polling, will be just like this, right? You will just take each 2x2 box and take the maximum as the output. And what's F here? I forgot. Yeah, I think this is F looks like it's padding. Yeah, it doesn't matter. We change the convention. I should just remove this slice here. It's kind of repeating what we're talking about. And finally, in a very kind of typical CNN, at least you think of the classic CNN, like you just alternating with this conf layer with value, of course, with the activation. And then after a while you do a polling, and then you repeat again, and then the polling, and so on. And eventually you typically have some fully connected layer. But also like this is kind of actually the fully connected layer is some of them now is people just do not keep that anymore. Okay, let me just go to one of these demo here, like that written by Kapafile several years ago. So this is like a complex demo. I think like it's using the architecture that is just a a very simple architecture. You can see like it have the original image here is like just a kind of a very tiny patch here. It's 32 by 32 by 3, and then you have actually you can modify this network, so it's like pretty nice. So you have the conf layer, right? Conf layer here, and the activation specified using Veloot here, and then you do a polling, and then conf layer again. I'm not sure that you guys can see it actually. Probably you can. Your eyesight is better than I do. So and then afterward it let's see. At the very end, you have a softmax here, right? Oh, okay. Here, like it did a second last layer. It did a filter with like 20 filters there. Then you have 20 output, but then you do a strike 2, you can't reduce to 10. And then you softmax, and then you have the number of classes is 10. And so you can see that how each layer is doing also, like, so this is the input, right? This input, and after the first conf layer, you can see the activation there, and also the gradient there, and the rate, and this is after Veloot. Actually, the first 2 layers you can from the activation see something, right? But in the later layer, it's actually hard to interpolate. Not interpolate, to kind of analyze what this activation actually means. We will discuss that, like how do we like check on like each what's this like activation mean like for each layer. Like if you want to going back to the original image, what if I activate some of this particular new one, what that new one's actually referring to. So we'll talk about that later on. Let's see. So you see like it does polling like a couple times, right? Like you did polling the first time here, reduce the size to 16 by 16, and then it do another polling to 8 by 8, and then do another polling 4 by 4, and then actually I missed a fully connected layer. Fully connected layer get to 1 by 1 here, and then you have and also 10 filters. So then do the softmax, and then you get this here. When open, this is already training, automatically training. You can see what's the accuracy right now. It's like 0.2, but I think like you can load load a p-string network here with 80% accuracy. Let's see if I can. Did it do it already? Okay, yeah, I think it did it already. So let's see if I. Now you can see like kind of correctly recognize some of this object here. So this just give the top 3 classes there here. So chip and so on. So anyway, like this is a pretty cool demo, even though this is kind of old, and also like it's convenient because you can play with it like pretty quickly. For example, if you want to change the letter here, you can just like, and this is like doing something local as well. Like it's just running on your laptop or like your desktop, and this actually didn't have any library. It's just doing JavaScript. So it's like something kind of, if you just want to impress someone that does not know anything about your network, then maybe this is a good things to demonstrate. So let me go back to, let me just stop it. It's kind of like use lots of CPU time. So we mentioned this letter by Lacune doing recognition that briefly at the beginning. So now you can go back to look at that. Like we just I just flashed this letter to you guys like at the beginning. But if you look at that, this is something really fancy, right? Now you know everything about that. You have a conf layer here. Then you have a downsampling. This is basically polling, and then you conf layer, downsampling, and then fully connected layer, and several fully connected layer. And it did really well for like digital recognition at that time. And then this is the Alex Lag that we mentioned in 2012 by the Hinton Group. If you look at that also, like it's pretty simple now to understand. You have conf layer, then have mass pooling. You have this so-called normalization layer now. It's not batch norm. It do this kind of, what's that called? Local response normalization. But I cannot remember the detail because no one uses it anymore. So, but if you're interested, maybe you can dig that up again. I don't know, maybe sometimes these old technologies will come back. But the idea there, they just want to imitate something like the biological new ones. The rough idea that normalization is that if you have the response, for example, like response like from a value layer or like for output from the value layer, so it's basically unbounded, right? So you may have like lots of the signals are all pretty big. And what they want to do is like they want to increase the contrast in this case. So they do a kind of special normalization, just want to make sure that like if everything is big and when one thing is bigger than like the rest, then you want to just increase the contrast somehow. But yeah, I mean, you need to get into the detail if you're really interested. But just my remark is like no one uses it anymore. So, but I don't know. You don't know. Maybe several years later, people find that it's actually useful again. And then like for the rest of the layer, it's just repeating itself. Like you have conf layer and mass pooling, and this conf layer, several conf layer, mass pooling, fully connected layer, and so on. And the latter looks a bit fancy. It's for historical reason. Just they use a GPU to train, but they don't have enough memory, so they kind of forced to split the latter into multiple pieces and then like trying to combine them again. So, but so this is again some of these tiny simple question to check your understanding. So the first column layer, they have the input is like 227 by 227 and 3 channel, 3 colors. And the first conv is a strike 4, have strike 4, and have 96 filters there, 11 by 11. So the output volume size, what's the output volume size?
Which should be 96 and 55.
Yes, 55 by 55 and 96, yes. So number of parameters, all close. Don't forget that 3 also. So it's like 11 by 11 times 3. If you want to accurate, you need to add 1 there and multiply by 96. And this is about 35K there. So let's see. Then second, you have a polling layer. So let's say the polling layer has strike 2. Strike 2 means that like, let's see, second is a second layer pole 3x3 filters apply strike 2. Yeah, this got me a little bit confused. Oh, okay, I see what they mean. This is weird. Yeah, okay. So we have a 3x3 apply strike 2. So then the volume is actually by half there. And what's the number of parameters there? Yeah, this is a tricky question. Or like, there's no parameter there, right? Yeah, because it's a polling layer. It's just like you're taking the maximum. Like, it's a little bit weird. You use 3x3. I'm thinking like, why? Maybe did they try 2x2 and 3x3 working better? I don't know. So they just take 3x3 and take the maximum there, right? So there's no parameters there. And then repeat themselves. Like you can do similar counting there for each of these layers. And you can count the number of outputs, count number of parameters. And there's some other details. Like they use Veloot. They are the first one to use Veloot, actually. So Veloot 5, I don't remember what Veloot 5 use now. Actually, maybe 10, actually, I don't know. So, but these guys are actually the first use Veloot there. They have this LOM layer, as I mentioned, but it's not common anymore. There's this local response normalization. They use all the data augmentations that we mentioned like last time, that you can just shift, like rotate and then scale, stuff like that. And they have dropout, like we discussed that already. Like, and they use batches. And stochastic gradient descent with momentum. At that time, they don't have atom yet. So, and then they have the learning rate is like this 10 to minus. They also like they don't have this like. This is kind of old school, right? It's like 2012. So they just have to fix learning rate or that step size, and then like reduce by 10 like, manually, like when the accuracy get to a plateau. And they also have rate decay. Do you still remember what's rate decay? Like,
It's hard for me.
yeah.
It's like you add something to the end of the document.
Yes, that's something to the cost function. There's
Yeah.
the you add that whatever the L2 norm of that parameter, say maybe I call it W, something like that, and the rate decay is this lambda here, something like. So you have the original loss, then you add that to penalize if your weight is too big. The parameters are too big, basically. And then they do some ensembles there. They basically just restart for, you can think of like you have different starting points and train the model 7 times and take the average, and then you can get some gain there. So the accuracy, the error then go to like 15%, something like that. Or this, as I mentioned, like they use the GPU doesn't have enough memory, so therefore they split the stuff like this in a fancy way. So at that time they are pretty good, like from the last year, like almost like really significantly improved the performance, especially consider the last year winner, like both of them use shallow network. It's just reduce the kind of the error rate by 3%, and this one go down to like 10% something. Then later on, like you have like all of this is neural network based. Like you have this CFLAT, and then like I think for CFLAT is very much similar. They just like change some do a lot of fine tuning. For example, like they changed this from like 11 by 11 to 7 to 7 strike 2, like and basically they just try to do a lot of fine tuning, just work out better. So I mean, like, it's not does not have like a significantly new idea, and also the VGGNet is like kind of similar as well, I would say. They have a deeper network basically, but I guess a contribution of the VGGNet is like they try to use smaller filters here. For example, you see they replace some of these like 5 by 5 and 11 by 11 filters by like layers of 3 by 3 filters. So the idea is like it's pretty common nowadays, like to replace like larger filters like with like stack of like smaller filters, because if you think of the what should I say, yeah, the support of the filter. For example, if you think of the support of like 7 by 7 filters here, if I have like cascade of like 3 by 3 filters, like 3 times, actually cascade of 3 by 3 filters 2 times, I will essentially get a support of like 5 by 5, right? And if I do it like 3 times, 3 cascade of like 3 by 3 filters is equivalent to a 7 by 7 filters. But for 3 by 3 filters, the number of parameters will be just like approximately 9 by 3, right? So I have 27 parameters here. But for 7 by 7, I will have like 49 parameters there. So you essentially have some gain here, like with reduce of number of parameters, and it turns out it's actually pretty significant. And you can even go for extremes that like have used lots of 1 by 1 filters. So as I mentioned earlier, you can because stuff is really volumetric, that 1 by 1 conv filters that's also like unlike in the classic cases is trivial here, like it's actually can do something for you. And this is like illustration for VGGNet. I'm not going to ask you to count this like the memory footprint and also number of parameters, but you can just see the number here. Actually, the model is pretty big. Like for each of the layers here, you have the number of parameters. One thing like a remark here is you see that like most of the parameters is concentrated in the fully connected layer here. That's why like you see the recent trend, like people actually want to remove the fully connected layers. And also, if you look at the memory footprint here, you have you consume lots of memory at the beginning, and then you have less consumption in memory. So it's kind of interesting that to see the parameters are concentrated at the very end, but the memory usage is at the beginning. And if you recall like what's going on for BAPOP, we cannot really release this memory until we do the backwork, the backpropagation of the gradient information. So when we go forward, you compute all these local gradient, and we need to store all this. So, and I'm I'm not saying that this must be bad, but this may be some reasons why, like the models nowadays is doing better, like in the sense that I think they are doing a better job to make it more balanced. So you in this VGG net really you have like lots of parameters are concentrated at the very end, but the memories are really using at the beginning. So you have lots of the outputs from the later are kind of concentrated at the very beginning. So that's VGG net, and any questions for you guys? I mean, I guess I probably will just stop here. So then you talk about the something like some two other kind of like very in particular Westlet, like it's more or less still the state of the art. Like many of the kind of model are still kind of based on Westlet. And so I guess I will stop here. And so do you guys have any
How long should we after?
oh, okay. It doesn't need to be long, so you can just a paragraph is enough.
One paragraph?
Yeah.
How much?
Oh, no, come on, this is not high school. Yeah.
Just one paragraph after.
Yeah, it's okay. Like, you put in enough information, right? You can even one sentence if you can manage to fit in all the useful information there, right? It's not about the length.
I'm not a big English speaker.
It's just like what do you want to talk about, just put it there.
So do we just say like I will introduce something and it will improve something. That's it.
Yeah, that's okay, yeah. Yeah.
We should this Saturday, right?
Yes. So, Tosa, any question here? Like, I guess yeah, I'm sorry, like I'm a bit late. I was a bit late today because I had a meeting earlier. So, but next time I probably can like start the collection earlier.
So when we do our presentation,
Yeah.
it can be more like application based, like than
Yeah.
like go over the library or whatever package we're using, but then we could like just show examples.
It's okay if
explain them in depth.
yeah, it's okay. Like you can get into all the details, right? I mean like yeah. I guess basically what I want to say is it's okay. Yeah.
We've been working like a week for biggest example or sample.
Yeah, I mean, like, I know it can take lots of time just to get it working. Like, that's totally fine. Yeah, and yeah, I'm definitely interested to listen to you, what you're talking about, like, for the dream. That's exactly reinforcement learning, right?
It is, yeah.
Yeah.
That's why I'm trying to implement like a sample DQN.
Yes.
It's mainly copying other people's code, but trying to get it to work with
Yeah,
my stuff. Since I haven't learned it yet, it's kind of hard.
yeah, it's okay. We'll talk about DQN actually.
But I mean, I already got some, like I got a random
Yeah.
brute force algorithm
Yeah.
that kind of does some video games.
Yeah.
But I was trying to get a nice one implemented to like
Yes.
kind of show it, but it's kind of a weird time because it's like TensorFlow went to 2.0, or they're going to 2.0, and I guess people didn't like 1.0 or the one version.
Yeah.
And so like OpenAI, who makes Gem and stuff, decided to switch to PyTorch.
Yeah.
And so all these extra, like Gem Retro and stuff, all these extra libraries are kind of on hold
Oh.
because they're going to switch to PyTorch. So it's like trying to debug a lot of stuff that
Yeah, I
isn't
understand. Like, I
quite
guess
working anymore.
does
'cause
it
it's
work
in
like
that.
for all the library? I guess I guess that's the reason. Like I don't know. Like do you use virtual environment? Like or do you use Linux at all? Actually,
I don't know.
you use Conda?
Mm-hmm.
Yeah, you use Conda. You use
I
Conda.
use Conda and Google Colab if it's something easy. But if it's
Yeah,
on my computer,
yeah,
that
Google.
one's-
Yeah, and everyone need to use Colab because at some point, you just need a GPU and yeah, maybe yeah, but if you
It limits you to like,
for a
If you
day
run-
something like
yeah, but if you run out of memory, it'll let you switch to high RAM mode, but it's only 25. And so like the first game I was doing was giving out frames of
Yeah.
like 210 by 160, which is still way too big, even though I'm only like buffering 4 at a time. And it was trying
Yeah.
to like allocate like 100 gigabytes of RAM.
I guess like
And so I had to like cut it down. to 80 by
honestly,
80.
yeah, I think that you're looking for games like the DQN like
Yeah, that
the
was,
lecture
That
paper.
was a Pong game from Atari.
Yeah, that one I don't know whether like
I mean, I got it
collab
working.
will be
I'm trying to debug it now, but I just had to like
Yes.
drop it down to 80 by 80. But you would think that like a 200 by 100
I
image is still
remember.
pretty small. It's like that big on my screen.
Yeah.
But it's still trying to. It's still, I guess, pretty big when it comes to machine learning.
It's I forgot like I can't remember the training for that one. It's still like need a lot of computations.
Yeah, it like does a table,
Yeah,
a rewards
I-
table
I-
for each action.
Yeah. So okay, yeah,
It's
that
more complicated than it should be. I feel like these libraries.
yeah, that's actually yeah, that's what I'm
They're-
saying. Okay, that's what I'm saying. Like I'm totally fine with you guys working on all directional project. That's the reason, because I can't say even I'm a more theory guy, but I start to do a bit more theory. But as it goes longer and longer, I realize that lots of there's a lot theory, and you can spend a whole several I don't know how many years just work on something really practical, like just figure out okay this Linux command or this and that. I'm like you can spend like suck so much time into that.
Mhm.
So therefore, like I appreciate all this effort. Like, of course, you can do derive this, that's totally fine. But you can spend lots of time on just making this work. And yeah, and that's basically almost like what DeepMind is doing. Right? I think lots of the stuff they're doing, the idea is super. Even like I guess I mentioned. I forgot, like, I mentioned to you guys, or I probably mentioned, like, for example, this XLLAT, right? That's a model, like, transformer. I probably talk a little bit about that, like, this language model, like, bird to the XLLAT. I watched a video about XLLAT. The final thing I remember is that, like, someone tried to calculate how much money you need to spend to train the model. They found that you need like something like about the cost of a house to just train the model if you can't train it on using like Amazon or like AWS or like
Electricity costs?
no they can't like what if you try to train the model on AWS or something that would be like or something like $200,000 or something like that. Yeah. So, but of course, this is a collaborator with like Google stuff like that. So, And of course, if you check with AlphaGo and all this, this is crazy, right? The amount of computations they use for. But therefore, like this is fun. But I guess if possible, like. If you are doing a PhD on this kind of stuff, then also you need to think about like, will your problem will be too much in terms of computations. But I don't know. Maybe you can budget on that. Maybe you can ask your professor to write a proposal, or you can write a proposal that to budget your computation for that. Anyway, but I don't know, like, so that's why, like, I think, for example, like I mentioned last time, this one fit one cycle, right? You try to train one cycle and go all the way and then go back down, stuff like that. So that's why this kind of work is so seminal, because it just can be used everywhere, right? And you kind of reduce the computation times for everyone, so if we can do something like that, of course that's great. Yeah, but many of these problems just have so many tedious details that just need to consider. So okay, I'm really going to stop now, and then